Welcome to our lecture on complex analysis. Today, we are going to explore two of the most powerful tools in mathematics, Taylor and Laurent series. These series allow us to take incredibly complicated functions and break them down into simple, manageable pieces. Let us dive in and see exactly how this mathematical magic works to simplify our calculations. To begin, imagine you are trying to sculpt a perfectly smooth, complicated statue, but all you have are basic, standard-sized clay blocks. If you stack enough of these simple blocks in exactly the right way, you can perfectly recreate the complex shape. A Taylor series is exactly like that sculpting process. It represents a complex function as an infinite sum of simple polynomial terms. For this to work, the function must be analytic, meaning it is smooth and has a well-defined derivative everywhere in a specific circular region. As long as the function behaves nicely in this solid circle, we can rewrite it entirely as an infinite polynomial. Now that we understand what a Taylor series is conceptually, let us look at its mathematical form. This formula builds the function outward from our chosen center point. The term f of z is the complex function we want to represent. We add up an infinite number of terms starting from 0. The numerator is the nth derivative of the function evaluated exactly at our center point, z0. We divide this by n factorial, which just means multiplying n by all positive integers smaller than it. Finally, we multiply by the polynomial building block, z minus z0, raised to the power of n. As n increases, these higher power terms bend the polynomial to perfectly match the true shape of our function. Before we move on, let us see this formula in action with a concrete example. We want to find the Taylor series expansion for the complex exponential function e to the power of z centered at the origin, where z0 equals 0. This specific case is often called a Maclaurin series. Our first step is to find the derivatives of the function at the center point. The exponential function is incredibly special because its derivative is always just itself. No matter how many times we take the derivative, the result remains exactly the same function. This unique property makes our job very easy. Continuing with our example, we now evaluate this derivative at our chosen center point, 0. Any non-zero number raised to the power of 0 is exactly 1. So every single derivative evaluated at the center gives us a value of 1. Next, we substitute our derivative value of 1 and our center point of 0 into the general Taylor series formula. The polynomial term simply becomes z to the power of n. Expanding the sum step by step gives us our final answer. This beautiful result means the complex exponential function can be perfectly calculated just by adding up powers of z divided by factorials, valid for any complex number in the entire plane. This brings us to an important question. What happens if our function is not perfectly smooth everywhere? Imagine trying to sculpt that same statue, but there is a solid steel pole right through the middle of your workspace. You can only sculpt in the empty space around the pole, forming a donut shape. When a complex function has a singularity, which is a point where it blows up to infinity or breaks down, a Taylor series fails. Instead, we use a Laurent series. A Laurent series introduces anti-blocks, which are terms with negative powers, to handle the explosion at the singularity. This allows us to safely represent functions in a donut-shaped region, completely avoiding the bad point in the middle. Now that we have introduced the concept, let us visualize where a Laurent series actually lives. Here we see the complex plane with real and imaginary axes. Right in the center, marked by a red X, is our singularity, z0. This is the danger zone, where the function breaks down. Notice the two concentric circles forming a shaded donut shape around the center? The inner radius is little r, and the outer radius is big R. This shaded area is the annulus. The Laurent series is only valid for points like z that sit safely inside this shaded region. It completely ignores whatever mathematical chaos is happening at the red x in the center. Having seen the safe region, let us look at the mathematical formula that makes this possible. This is the full Laurent series formula, and it comes in two distinct parts. The first sum, with coefficients a sub n, contains the positive powers. This is called the analytic part, and it behaves exactly like a standard Taylor series, describing the smooth part of the function. The second sum, with coefficients b sub n, contains the negative powers because the variable term is in the denominator. This is the principal part. As the variable z gets closer to the center z0, the denominator gets very small, causing these negative power terms to grow extremely large, perfectly modeling the blow-up behavior of the singularity. Let us apply this new formula to a function that is broken at the center. We want to find the Laurent series for the function 1 over z times z minus 1, centered at 0, specifically in the ring-shaped region where the magnitude of z is between 0 and 1. First, we identify the singularities, which are points where the denominator is 0. These occur at z equals 0 and z equals 1. Since our region is strictly between these values, we are safely inside the annulus. To solve this without complex calculus, we algebraically rearrange the function. We factor out 1 over z and factor a negative sign from the second part to get negative 1 over 1 minus z. Following our algebraic rearrangement, we can now use a clever trick. The fraction 1 over 1 minus z perfectly matches the standard geometric series. It is a known mathematical fact that as long as the magnitude of z is strictly less than 1, which fits our given region perfectly, this fraction equals the infinite sum of 1 plus z squared and so on. Now, we substitute this infinite geometric series back into our rearranged function. We still have the negative 1 over z fraction sitting out front, waiting to be multiplied into the series. This approach saves us from having to calculate complicated derivatives. For our final step, we distribute the outside term, negative 1 over z, to every single term inside the parentheses. When we multiply it by the first term, 1, we get negative 1 over z. This is a negative power, which forms the principal part of our Laurent series, capturing the singularity at the origin. The rest of the terms become negative 1, negative z squared, and so on. These form the analytic part with positive powers. This final expression is our complete Laurent series, successfully describing the function in the donut-shaped region around the singularity. Now that we have calculated these series, you might wonder why they are so important. Taylor and Laurent series are the absolute backbone of advanced engineering and physics. In real life, computers cannot actually compute complex functions like sines or exponentials directly. Instead, they use Taylor series to turn these impossible functions into simple addition and multiplication problems that a microchip can process instantly. Laurent series take this a step further. They allow engineers to analyze systems that have points of failure, like a bridge vibrating at its critical frequency. By isolating the principal part, engineers extract a crucial number called the residue, which magically solves incredibly difficult integrals in quantum mechanics. Let us wrap up by reinforcing the most important ideas we have covered today. First, a Taylor series breaks down a smooth, well-behaved complex function into an infinite sum of simple polynomial building blocks. Second, when a function has a broken point or singularity, the Taylor series fails and we must use a Laurent series instead. The Laurent series adds negative power terms, known as the principal part, to safely handle the explosion at the singularity within a donut-shaped region. Together, these incredible mathematical tools turn impossible calculus problems into manageable algebra. You have now mastered the core concepts of Taylor and Laurent series.